Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Thursday, March 31st, 2022. I'm delighted to be here with Dr. Denise Caldwell. Denise, it's great to be with you. Thank you for joining me today.
Well, thank you for the invitation
Denise,
and
to
the
start,
opportunity.
would you please tell me your title and institutional affiliation?
Okay. My name is Denise Caldwell. I'm the Division Director of the Division of Physics at the National Science Foundation.
Denise, do you have a background in physics?
Oh, yes. I have a PhD in physics, which I got from Columbia University. After finishing my PhD in physics in experimental atomic, molecular, and optical physics, working with what's known as photoionization using higher energy photons, I then completed a postdoctoral stint of a little over 2 years in Germany at the University of Bielefeld. I returned to the US and taught for a time at Yale University on the Faculty of Physics, where I started a research program in photoionization of atoms and molecules that was funded by the NSF, actually. Then I moved to the University of Central Florida, again to the physics department, where I continued my NSF-funded research and also was contributed a lot of time to the development of what was at that time CREOL, or the Center for Research in Electro-Optics and Lasers. That is now a separate unit within the University of Central Florida.
I've interviewed Peter Delphiet. I've learned all about Creole. It's wonderful.
Oh, yeah. I was hired to UCF when Creole was just established. And so I spent about like the first 5 years of my time at Creole, time at UCF, really spending a lot of time pulling Creole together, working with the local laser community, working across colleges at the university. We hired the first director. We hired some of the first faculty. It was a very heady experience. And I can honestly say I really like to build things. I like to pull things together. I like to get things started. I like to see them. And it's really, I left UCF when I came to the NSF in 1995.
And what were the circumstances of changing career course and joining the NSF?
Well, I had a productive period as a professor, right? I had a research program, an ongoing research program. I had students, I had postdocs, I had collaborations. It was very active. And but around 1995, I had got to a point where we had completed the research emphasis that we had been working on. And I was thinking, where do I go next? What areas would I like to go into? And I got a phone call from someone I knew who was a program director at the National Science Foundation in the physics division, asking me if I might be interested in coming to the NSF on a temporary basis as what's known as an IPA, under the so-called Intergovernmental Personnel Act, I think is what it stands for. This would be a temporary assignment to work and manage the program in the physics division in atomic, molecular, and optical physics. And I thought, I've kind of come to a turning point. So where do I go from here? And this just came out of the blue. And so I was offered the opportunity and I decided to take it.
And Denise, I'll just note that at this point in your career, you were already very appreciative of the way NSF can support fundamental science.
Oh, yes, yes, yes. I would say that my scientific connection to the National Science Foundation started when I was a junior in high school.
Oh, my goodness.
because the reason was at that time NSF had a program called Summer Science Training Camps. They were funded by NSF at universities across the country. And the idea was to bring in promising high school students between their junior and senior year in high school to essentially spend 12 weeks in a summer science training camp. And I call it boot camp because I'm telling you, after 12 weeks of that, you knew what you were getting into if you went. There was no doubt about it. And so I did that. And it just, oddly enough, that particular training program was in organic chemistry and molecular biology, which was, it was at I grew up in Mississippi. It was the University of Mississippi, so it was close, reasonably close by. But it turned out that was the only course in biology I ever took in college. But later on in the physics division, I actually established a program in the division that's now called Physics of Living Systems. But it was making the connection between physics and biology. And the little biology that I knew or could learn, I took from that summer science training camp. Anyway, a little bit now to how I got to, yes. So I knew what NSF could do. And so it was, coming here was then an opportunity to actually, I viewed it at that time more of an opportunity to see where the field was going. Because I thought, if I go to NSF and I have this position, I will be able to see everything that's going on, right, across the board. And this would be, it would help me think about where I would like to go from here. Well, I arrived in the summer of 1995, the same year and the same time that Carl Wyman and Eric Cornell had demonstrated Bose-Einstein condensation in atoms, right? And that was in my program. It was in this program. This was closely followed by Wolfgang Ketterle at MIT, again demonstrating Bose-Einstein condensation. So it was a heady time. And all of this was right smack in the middle of my program. I also arrived when NSF had started a program in optical science and engineering. It was an NSF-wide program covering all of the divisions, all of the recruits in NSF. And literally one of the first examples of an NSF-wide activity. And I replaced the person who had been heavily involved in establishing this program. And so I took over where he had left off. And it was a wonderful experience because I got to know everybody throughout the foundation. Since it was an NSF-wide activity, I met program directors from all of the directorates in all fields, biology, computer science, engineering, and it was intellectually, it was just really, really exciting. And that combined with the fact that my program what was going on in my program was changing the whole field. And so it was just, and the division director was very supportive was really excited, first of all, about Bose-Einstein condensation and really supported the program. And when the opportunity came to stay, I decided to take advantage of it. I really enjoyed it. It was a wonderful place to work. The other program directors I worked with, every one of them was willing to go beyond, just do whatever they could for the benefit of the community. And to a certain extent, it's a real service to the community that individuals who are willing to devote their time and their expertise to promoting what they see coming from the community as the most exciting scientific projects. Mm-hmm. And so I decided to stay. And when the opportunity, I applied for the position, got the position, and then went on from that point to not only AMO, but I worked a lot in plasma physics. And then I established as I mentioned, the Physics of Living Systems program, working with molecular and cellular biology, drawing on these connections that I had made in getting to know people and getting to know other areas. I established what is now the Physics Frontier Centers program. Again, working across multidisciplinary types of areas. I spent a lot of my time doing that. And I have always found it extraordinarily rewarding to interact really across this spectrum of science, from, because physics does reach out and touch pretty much to just about everything at some point. And so it was the right move. I really, really enjoyed it. The opportunity came to apply for the deputy division director position. And I was recruited for that, to apply at least, and then moved on to division director in 2013, something like that.
Denise, to set the stage, in the late 1990s, were you aware of what people like John Preskill and Alexei Kitaev were doing at the very dawn of quantum information?
I certainly was. And I looked a little bit at the history, of what I remember. And in 1999, NSF sponsored a workshop on quantum information science. Okay.
Do you know who got that going? Who at NSF was behind the sponsorship?
One of the primary movers was the division director of the physics division at that time, Joe Damer. Right. Joe also came from a background of AMO physics and had come to NSF from NIST, right, where he had worked in the physics laboratory at NIST. And so this was, first of all, I should say that, the people I was funding at the time, people like Ketterle and Cornell and Wyman, and probably almost more than anyone else, Jeff Kimball was in my program.
So you already had Caltech on your radar at that point.
I knew I had Caltech on my radar, right? And I think Jeff had started at UTexas Austin, but I think by that time he was already at Caltech. Mm-hmm. But I funded Jeff through the AMO program essentially more in the quantum optics area, not necessarily precisely in QIS.
Do you remember specifically what Jeff was working on at that point?
I tried to thumb back through, but we don't have any paper anymore.
But it was definitely quantum optics stuff.
It was quantum optics, right? I think the one thing I remember Jeff really working on, and I think it was from this period, was QED and high performance cavities, mm-hmm. resonance cavities, right? Whereby I can remember, I think one of his activities was building these really, really, really high finesse cavities so that you could almost contain like one photon in the cavity. It was really pushing the limit of what you could do with these really high finesse cavities for quantum electrodynamics. I would say that's probably the area that I most recall that he was working on at the time. Mm-hmm. Right. I probably the defining point when it started to move over in quantum information science was in around 2000. Mm-hmm. And there was, again, one of these NSF-wide activities in the year 2000, roughly, 2000, called ITR, Information Technology Research, was the, global name of this program.
And this was an NSF program?
This was an NSF program, Information Technology Research, ITR. And ITR focused, as I said, it was a very broad spectrum. There was a lot of focus, information technology. So there was a lot, the primary focus, I would say, was probably on big computers and data analysis and the type of things you normally associate with sort of more classical computing and classical data needs. But there was a small little fraction of that program that was pushed by a program director whom I knew very well at that time in the computer sciences directorate, that was dedicated to quantum computing.
Denise, was there partnership with the DOE and their interest in supercomputing for ITR?
Not to my knowledge, but I was not heavily involved with the heavy-duty, high-performance computing side of the house, mm-hmm. right? I got into it through the quantum computing side mm-hmm. of the house, right? Because this is a lot of what you hear about quantum information science grew out of AMO physics, I would say just atomic and optical physics, let's say primarily. The types of things that Jeff Kimball was doing at the time and others, and condensed matter physics. And that's where the emphasis was in these really preliminary areas that ultimately sort of started to collect until this whole notion of quantum information science began to well up as an area of particular interest.
Now, when the IQI got started at Caltech, mm-hmm. when John Preskill and Jeff Kimball and others started to have this idea of formalizing this collective mm-hmm. excitement over quantum information, mm-hmm. was the NSF involved in that, either formally or informally in any way?
Well, remember that the NSF really responds to proposals.
Right.
So we don't specifically work with in an activity like this. We don't work with any particular institutions per se, but what we do is we try to identify, based upon conversations with members of the community, conversations with people like Jeff and people like John and other members of the community whom you could name, people like Paul Kwiat at Illinois, people like Misha Lukin at MIT, Chris Monroe, Dave Wineland. This is the community who's really moving this field forward. And so we listen to that community. And it was listening to that community across this broad spectrum of high performance computing and things related to it that led to ITR. So NSF then looks at where the science is going. And we ask ourselves, what do we see that seems to be an area of research whereby if you put in a sudden influx of resources with emphasis, you can really make a big advance, right? And so this is where things like that's where the original optical sciences and engineering came from that I was involved with. It's where the whole nanoscience program at NSF came from. And it's where the ITR program came from, right? And so it is the recognition, and it is, you know, what we hear the community and people like Jeff and John and the others I mentioned in the community are telling us that this is an area that really is ready. It's sort of ripe to move forward. It's starting to coalesce, and so this is how I would say this is more or less that there wasn't a direct connection between NSF and the Caltech or any of these that set it up, but the recognition from what we're getting from the community that this is an area we should be promoting. Then once we make a decision that this is an area that to be promoted, then we create something like an initiative, something like ITR or Nano or the others that we've done, and we issue a call for proposals. And this is a wide open call. It's not restricted to any particular institution. It's just a wide open call. This particular one, if I remember correctly, there was a component of this call that was sort of at the institute level. There was an individual investigator, smaller proposals, and then there was the institute level. And I think Jeff, I believe at the time, was the PI. He was the leader or listed as the PI. John was the co-PI, I think, at that time, for the IQI. And so they competed in an open competition and got the award. And that started off the IQI. Now, a program like this typically will run for 5 years. So there was an award up to 5 years, and then something else will come along for a big initiative. But at the same time, what do you do with what you have started? And so in the physics division, I was instrumental that time in getting a program established in quantum information science and revolutionary computing as a separate program within the physics division. Just like particle physics and gravitational physics, this is quantum information science. And so once the institute had completed its 5 years, and then I think it was John who took over and submitted a proposal to this program for the continuation of what they were doing. Now, it wouldn't be on the big institute level because it wasn't the same amount of funding, but we did co-fund that with the Computer Science Directorate. So we funded that for maybe 2 cycles, I think, led by John. And then the physics division created the Physics Frontiers Centers program. That had been created in 2000, but Caltech, I think it was still Jeff at the time, submitted a proposal to this Physics Frontiers Centers competition. And I can tell you, it is brutal. It is a brutal competition. and they were given the award, right? And then they were been given a renewal. So this is a little bit the history of the evolution of what's the IQIM now.
Denise, how did IQI in this initial brutal competition come out on top? What was so compelling?
Science. Okay, the Physics Frontiers Center always starts out with frontiers, physics frontiers. The word frontiers is aptly chosen because it really has to be at the cutting edge of physics, right? we fund a lot of really, really good stuff in the physics division, but there's certain areas, and all of our programs to a certain extent, to a great extent, push the boundary. But there's some that are kind of more or less ripe, whereby, again, it goes back to this is an area that is ripe, and an extra influx of funds on a larger scale can make a very big difference.
Denise, was the impulse at this time to support quantum information as a theoretical pursuit, or were people already starting to talk about actually building scalable quantum computers?
Both. Both. Right. But not just computers. I mean, there are a number of other areas.
Quantum sensing, things like that.
Quantum sensing, right? I mean, the physics division, we have a big program in quantum sensing. A lot of our QIS is related to sensing. Some of our AMO is related to sensing. So there's quantum sensing. And there's, and then there were all of the issues with quantum networking and quantum communications. Now, within physics, we have mostly been connected to the quantum sensing and the quantum computing part of it. And so you ask, how did a proposal like this move to the, first of all, it has to make the argument that this is a compelling scientific frontier. And it is sufficiently compelling that it warrants and will move ahead more quickly with a center level investment of funds.
Denise, if we could zoom out where it's not just the science that's compelling, but for the NSF, the determination that the science should be supported because it's in the national interest. I wonder if you could talk about it from a sort of macro political perspective.
I think there are two answers to this. Okay. And the first one comes at I'm going to call the basic fundamental level. Okay. And the basic fundamental level is pretty much where we are by now. Because we're right up to, I'm going to take us, chronologically speaking, up to about 2008, let's say, something like this. Okay? And whereby you've seen progressions in this understanding the science. Okay? You're really beginning to look at, see what can you do? What are the possibilities? And in 2008, I think it was released in 2009, there was someone, Carl Williams from NIST, was over at Office of Science and Technology Policy, and we prepared a report on the potential of quantum information science for the future, because the idea of quantum computing had been around, but everybody had nixed it. Everybody had said, it'll never happen. You've got so much decoherence, you'll never build anything that's going to work like this, right? Sensing is on a slightly safer ground because it's really kind of measurement, right? But quantum computing was bad. It's like cold fusion. It'll never happen. And but around 2008, we issued this report. And this was followed up by a workshop that was led by John, actually. He agreed to co-chair this workshop in 2009 that NSF sponsored. And to just go back and revisit the potentials for quantum information science. And there's a report that John and company wrote. And all this time there was an activity at OSTP. I was a executive secretary, I think, for a working group. in the area of QIS. The difference came between, I would say, roughly that time, that workshop, and I'm going to say about 2015, because the technological advances that we see during that period in what you could actually build, and also in other areas like quantum simulation, and what you could actually realize. You saw, for example, the ion-based computers that people were starting to assemble. And so there was sufficient technological advance between, I would say, 2009 and 2015 that suddenly opened everybody's eyes that this is not just somebody's imagination, but there are some real possibilities here.
What were those real possibilities? What jumps out in your memory?
I would say probably the first, some of Chris Monroe's and Dave Wineland's work at NIST before Chris moved to Michigan and then on, that you could actually potentially control these states. Quantum control, if there's a difference between the pre-QIS area time frame and that QIS era, I would say the difference is quantum control.
And this distinction, this would be basically pre-2000 and post-2000? Is that the demarcation roughly?
I would put it closer to 2010.
Uh-huh.
Okay, because people have been working on quantum control.
Right.
Up to then.
So what were some of the advances from 2010, from 2000 to 2010 that makes that point this dividing point?
I think I would say better lasers.
Better lasers, interesting.
Right. Just a better, and it's not one thing, right? Because all of these things had existed before, right? But you knew how to make cold atoms, mm-hmm. right? But you had such control over your lasers and over your traps, for example, that you could at will generate a predetermined state, right? And then have detection capability that allowed you to monitor that state, either by probing with other lasers or by just watching a Bose-Einstein condensate fly apart. It's not any one thing, but probably the time where the things that people had been looking at kind of began to work on a global scale, mm-hmm. right? That it wasn't just one really refined thing in one particular area that could do something, but there were lots of things you could possibly think about. And so you really, because if you want to build a quantum computer and you want it to do something, you got to know what your input is. Mm-hmm. That's where control comes in. And to try to describe it without going into technical terms, I've been working on trying to do this for a long time, and I've never really totally succeeded. But we talk about, what do we measure? Okay, let's suppose you do an experiment and you have an atom and you let it collide on something and you look and see where it is afterward. What you typically measure is a probability. That is, you just detect it, right? But you don't necessarily measure a lot of fine details. But for quantum computing, you got to know those details. So what you need to do is it's not just enough to know where the thing is. You've got to know what it actually looks like. And this is really an understanding of the quantum state, not just, well, I know that it's here, and if I look, I'll see something. But I know that this quantum state has to be at this point, and I can read it out. And the whole idea is that this state, right, I create it here, and it goes its own way, and I test it here. And how it goes from here to here, and what happens, that's quantum evolution. So if you think about it in the Feynman terms, this is his interpretation of quantum computing. Mm-hmm. That is, but it only works when you can create in advance with pre-knowledge that very, very well-defined state. And you can hope that you can put that state in somewhere that nothing can influence it, okay? That it just can go off and do its thing, and then later on you can see this is what it did. That process is actually a calculation, mm-hmm. right? And so you go from one to the other, and it is, but you can only do it, like I say, you can only do it if you can know exactly what you have created to start with. And I would say that it wasn't any one particular new thing, but the fact that all of these approaches to control, to confinement, to the reduction of interferences had just improved to the point at which you started to notice a real difference.
Denise, what were the laboratories doing laser research in the early 2000s that were really at the vanguard of these improvements?
Well, there were a number of them. I would say, first of all, there was Caltech, right? And
who at Caltech? Who was doing this at Caltech?
It was Jeff. It was primarily Jeff,
uh-huh.
whom I knew, right? I don't know whether Oscar Painter had arrived there by that time or not. He came more or less from the condensed matter physics side of the house, so I was not, that well acquainted with him. Of course, I knew of Alexei Kitaev from the theory side of the house.
Right.
But experimentally, it was John, and theoretically, experimentally, it was Jeff, and theory, it was John and Alexei.
And what was your sense of how these experimental advances were refining and improving the theory in quantum information?
Well, I don't know, because I would have to say, I think, if you go back to Alexei, some of those first papers, and Jeff also did some theoretical work. To a certain extent, the ideas were there. The ideas were there, right? And if you think about Alexei's papers, I mean, these are the seminal notions, right? And people like Alexei, Peter Sola, who had been at NIST for a while and then moved to Europe. The theory or the theoretical notions were really alive right? I think the real breakthrough was the experimental realization. Because if you're going to actually build something, you've got to realize it experimentally. And this was always the criticism. You can talk about coherence as much as you possibly want, or lack of no decoherence. But until you can actually build it, it's not going to be good for very much.
So this proof of concept that ultimately forms the seed for the IQIM, Are you following this in real time? Are you aware of these connections even before this decision and the proposal arrives at the NSF?
Oh yeah. I mean, I have been involved since 1999.
So what's the mode of connection? Are you coming to seminars? Are you on email lists? Are people just sort of like messaging you, "Hey Denise, we've got amazing stuff going on"? How are you keeping tabs of all this excitement?
Okay, well, a number of ways. First of all, my programs. All right? Because I had the program. These proposals were coming to my program, right? And so this is really the first way that we at NSF get informed of where the science is going, are proposals we get. So, and that's what the proposals were doing, right? And so I had the proposals to keep me informed, all right? I had the reviews of those proposals, which meant that I had the expert advice of people in the community who knew something about this. Right. So that's number one. Number two, I would go to, the regular meetings like the DAMOP meeting, the Division of Atomic, Molecular, and Optical Physics meeting. I represented NSF at these sorts of things. And then as an outgrowth of this first involvement in optical sciences and engineering, I was involved across the board in NSF activities that ultimately were related to this in one way or another. I mentioned I established the QIS program in the physics division. So now I had proposals coming in just for QIS. So I had those. I kept in very close touch with colleagues in particularly in NIST, with Carl Williams at NIST. I knew Carl extremely well, and Carl has been a promoter of QIS since the very beginning, right? He recently retired, and as he commented, for over 20 years, he and I have been partners in crime, right? Promoting QIS within the U.S. government. So I interacted closely with Carl. And then, as I mentioned, when Carl went to OSTP, I was heavily involved with writing this document that we first issued. I was executive secretary of the working group. We held meetings with other agencies, right? We would hold there was a man by the name of Henry Everett at ONR. He was in the Army, I think. And he used to organize these regular meetings of all of the government agencies who were interested in quantum, in QIS, right? And I was the NSF representative to these meetings. And so I knew what the other agencies were doing. I knew what they were saying. It's just been, I've been sort of knee deep in it for well over 20 years now.
Denise, where is quantum error connection in all of these developments? Because in order to have the IQIM as a viable project, there needs to be sufficient optimism that quantum error correction is something that can be dealt with effectively in the long term.
Yes. I think John working, again, this is something that we supported, I think, through, if I remember correctly, through the physics division, because we funded what's now the Kavli Institute for Theoretical Physics. And if I remember correctly, John headed up a workshop there way back when on quantum error correction to just see, could it be done? Could it be done? And it's important. Maybe I differ a little bit with John on this one, but he's the expert, so don't take my word for it. He knows a lot more about this than I do. I think quantum error correction is important, but I worry a little bit, and this is a little bit, as I say, my own philosophy. I think we make a mistake if we start to think of quantum computing in the same way we think of classical computing. Mm-hmm. I mean, one of the things that I learned was that programming a quantum computer is totally different from programming a classical computer. This is one thing that makes it difficult, right? Because, and it's not just that for quantum computing, classical computer, you got a stack, right? You got this machine on the bottom, and then you got a couple of layers that gets to the user. And so the user writes a program. Somebody has written a compiler. That compiler takes that program, converts it into machine language, and the thing goes back and forth. So it's the computer stack. That doesn't exist for quantum, right? And so the challenge is for the field, is how do you get from the machine to that user who doesn't care about the details of the machine, right? They just want an answer to the problem. But quantum computing is not there yet. Developing the stack is very difficult. And one of the things that I have learned, at least if I understand correctly, is that making the connection between the algorithm and the machine may involve a lot of manipulation of the stack as well. So it's not like you can just do what you do with classical computing right now, but you really have to think of the stack as a whole. And I think a lot of the work is, a lot of the thinking is to, how do you build the stack? Now, error correction. Error correction, we know how to deal with in classical computing, right? You just do a repetition. Well, you can't do that in quantum, right? And so the idea is, and John had it, the proof is that it can be done. Mm-hmm. I think, and there are some companies who are really focused on error correction. I say, if we can do error correction, then, we know that it can be done. Theoretically, it can be done. But how do we implement it? The difficulty is that when you start implementing error correction, the number of qubits you have to add to the system grows rapidly, right? Just in order to do it. And so I think and here again, I'm not the expert. I am not a computer scientist. And I would defer to what John or Alexi would tell you about this. But I think that what we might see happen is that error correction in quantum might look a little bit different. I don't know that, right? But it's important. I mean, from a computational perspective, you've got to trust your system. And so error correction, knowing that there has been no decoherence, is going to be critical. Or that if there is, how much it is. That's going to be really, really critical. And all of this is connected to fidelity.
And when you talk about critical, just to be clear, there's a very solid line between resolving the problem of quantum error correction and actually building a scalable, even commercially viable quantum computer.
It could well be, if in the end, the only way you can handle the decoherence question is through error correction.
But there might be a way around that, you're saying?
There might be. I mean, I think that there might be and there might not be, right? But we have, for example, and John will tell you this, that there are the so-called NISQ machines, mm-hmm. right? Noisy intermediately noisy intermediate quantum systems, or NI, anyway, whatever, NISC. John will tell you what it means. But these are machines that are noisy. And so the community now is trying to ask the question, what can we do with noisy machines? Mm-hmm. Can we actually perform a reliable calculation with noisy machines? Right? And now people are really working on that and trying to just see, what can we calculate? If you can calculate something with noisy machines, then you can think about, probably at the scientific level, doing some, making some progress in doing some real science with just the noisy machines. However, if you want to go to the universal machine, so are you thinking about a machine that a scientist would use in a laboratory by, taping and twiggling and making it work, right? Which is usually the first step. And something that your general user can use, the universal quantum computer, right? And probably for the second one, I think it's in the second one that error correction is going to be most critical.
All right, Denise, so this is an extremely important point, and I think this will be our last question for today's session. There's so much more to talk about. Hopefully we can meet back again.
Yeah.
It's an incredibly important observation you're making. So if I'm understanding correctly, what it sounds like you're saying is that ultimately the proposal and the successful pitch to NSF to jump in and support IQIM with both feet is that for NSF institutionally, having a game plan to demonstrate that quantum error correction is resolvable is not really a hang-up. In other words, you don't need to see that perfect pathway from getting to where the field was in 2010 to however long it's going to take that says, if you can demonstrate that quantum error correction is a resolvable problem, then we will support this. That was not part of the calculus.
And that was, the question that I'd have to go back and get John to show you the proposal. But we weren't, even in those days, we weren't that far along. It was just the proposal was just like in all of the Physics Frontier Center's proposals. The proposal would have to be, say, this is a cutting edge area of science. It's the cutting edge area of physics. We know a lot. We have got the right group and the right team, and we've got it appropriately put together, that we will significantly advance this field.
But it's about fundamental research and not translation.
That's right. It's about physics. But there's one other part of the Physics Frontier Center's program that you can't forget.
Yeah.
And that is the workforce preparation part. All right? Because that proposal and what they would have to demonstrate was what they would do and how successful they believed they would be in training the next generation of young people, mostly young, who would move this field forward.
Because this is a multi-generational scientific effort.
If it's a frontier and you're on the edge of the frontier, you might push the boundary.
Right.
But frankly, you're probably not going to be around to see where it's going to go.
Meaning that in 20 years, graduate students will still be excited about this.
That's right. Right. And I think you see that, right? I think you really see that. You go to some of these PFCs, and I've been out to the Caltech one a couple of times, right? And the students are bouncing off the walls.
That's right.
They're just so excited about this, right? And they really get, I mean, this is what you have to have.
Right.
And this, I would say, is when it comes to our Physics Frontiers centers as a whole, I would say that this is one of the most successful aspects of all of the centers. That you go to a meeting, when we do our reviews, our periodic reviews, you go out there and we always meet with the students. We kick all the faculty out and have a meeting with the students and postdocs. And the level of excitement and the ability is just amazing.
Denise, on that note, it's a perfect place to pick up for next time, where we'll discuss the actual ideas that came together for the proposal to make IQIM.